So on this one, chapters 8 and 9, we're dealing with sampling distributions and confidence intervals. So we have our formulas up here. For AP, I'm not quite sure that these are on the formula chart, so you may need to just know them, but they may be. That would be something to look into, see if they're there or they're not. Okay, so for the first one, in one region of the country, the mean length of stay in hospitals is 5.5 days, with a standard deviation of 2.6 days. Because many patients stay in the hospital for considerably more days, the distribution of length of stay is strongly skewed to the right. Consider random samples of size 100 taken from the distribution with the mean length of stay, X bar, recorded for each sample. Which of the following is the best description of the sampling distribution of X bar? Okay, so if we remember from, this is a chapter 8 question. We remember from chapter 8, we said that the mean of the sample means is equal to the population mean. They told us this mean was 5.5 days. That's what this one would be, 5.5 days. Then the standard deviation of the sampling distribution is the standard deviation divided by the square root of your sample size. But they give us 2.6 as our standard deviation. Sample size is 100. So I'd have to do 2.6 divided by the square root of 100, which is 0.26. So that's going to be our mean and standard deviation. What we can do at this point is go through and see if there's any we can throw out just based on these values. So the means all look good. That one's no good. It's good. That's no good. That's no good. So A, C, and D can go. Now, if we have sample sizes of 100, what does that tell us about the shape of the distribution? It would be approximately normal. So we wouldn't be skewed anymore. We would reach normality. So E would be our answer. Because our sample size is 100, so we're by the central limit theorem. Remember, the central limit theorem says that if n is greater than or equal to 30, we approach normality. We can start approaching normality. So here n is 100. 100 is greater than 30, which makes it approximately normal. Does that make sense? Okay. Number 2. Notice, before even reading the question, notice that you don't have to calculate anything. You just have to set up the formula. The management team of a company with 10,000 employees is considering installing charging stations for electric cars in the company parking lots. In a random sample of 500 employees, 15 reported owning an electric car. Which of the following is a 99% confidence interval for the proportion of all employees at the company who own an electric car? We're dealing with a proportion here, which means we need to get p hat. So what proportion of these employees own electric cars? 15 reported it out of the 500 they sampled. So 15 divided by 500 gives you a p hat of 3. Which means I can throw D out and D out. The proportion is wrong. Okay, now let's get our critical value. We want a 99% confidence interval. So there's a couple of different ways. If you did what I recommended and you memorize the value, and B. Z critical is 2.575, or somewhere close to that. So that means we could throw A out because our Z critical is incorrect. Now let's say you didn't memorize them. You didn't want to have to memorize the 4 values. The other thing you could do is find the probability that Z is less than 99.995. That's going to be your Z critical. .576 according to the instructions here. Okay, so now we're down between C and E. Well, how do we get our standard deviation for a proportion? Square root of p hat times 1 minus p hat over n. Which we said p hat was 0.03. 1 minus p hat would be 0.97 over 500, and that's what we take the square root of. So, which one of the 2 remaining have that as our standard deviation? Certainly not E. So C is correct. Okay, number 3. A school administrator is interested in estimating the proportion of students in the district who participate in community service activities. From a random sample of 1,000 students in the district, 100. Where I got the 1,000 from, I have no clue. From a random sample of 100 students in the district, the administrator will construct a 99% confidence interval for the proportion of all district students who participate in community service activities. Which of the following must be true? So, yes. So A says that the population proportion will be in the confidence interval. Does it have to be in the confidence interval? No. No, it doesn't have to be in the interval. Remember, there's still a chance that it's not. A is out. B, the probability that the confidence interval will include the population proportion is 0.99. We're doing a 99% one, so could be. C, the probability that the confidence interval will include the sample proportion is 0.99. Do we care about sample here? No, we're always interested in population. So that sample one can be, that word sample throws it out. The C can be eliminated. D, the population proportion and the sample proportion will be equal. No, definitely not that one. E, the probability that the population proportion and the sample proportion will be equal is 0.99. No. So our answer is C. Okay, number 4. The State Fisheries Department wishes to stock the Styx River with fish and would like the species to not only survive, but thrive. The substrate of a river is an important determinant of the quality of spawning habitat. The pebble diameters in the river are approximately normally distributed with a mean of 24 millimeters and a standard deviation of 8 millimeters. The fisheries will select a random sample of pebbles from the Styx River in an attempt to judge the average pebble size. What's the approximate probability that a sample of n equals 16 from this population would result in a sample mean greater than 30 millimeters? Okay, so we're dealing with sample means. We're going to have a distribution of sample means. Let's make note of what we know. We know that mu of x bar has to be equal to the population mean. And what did I say the mean was? 24. The standard deviation of population, of sample means, is the standard deviation divided by the square root of our sample size. So that's going to be 8 divided by the square root of 16, which is 2. And what they actually are interested in is the probability that x bar is greater than 30. So to get this, we need to standardize. We have the probability that z is greater than 30 minus 24 divided by 2. Which is the probability that z is greater than 3. Just 1 minus the probability that z is less than 3. If we look that value up on our z table, we would get 9987. So our probability would be 0.0013. Questions on that one?
What does this entail again? Chapter 9?
This question is a chapter 8 question. Because we're dealing with a distribution of sample means. Okay, next one. The first large-scale study of the human sex ratio involved over 6,000 families, each having 12 children. This was done in 19th century Germany, and large families were more common then and there. 52% of children they observed were boys. Suppose that 21st century researchers wish to replicate this observational study. In order to see if this proportion of boys might have changed in the intervening years, suppose researchers tracked down 50 families with 12 children. From these 600 children, a random sample of 50 children is taken. 30 of the 50 children were boys. Part A asks us to show that it is reasonable to approximate the sampling distribution of P using a normal distribution. Okay, so the first thing we need to do is figure out what P hat is. We're told that N is equal to 50. But how would I get P hat? Let's say boys are a success. 30 over 50. Which as a decimal would be 0.6. So to show that we can approximate it using a normal distribution, we have to look at N times P hat and N times Q hat. Q is just 1 minus P hat. So 50 times 0.6 gives you 30. Is that greater than or equal to 10? Yes. Then I have to do 50 times 0.4, which equals 20. Is that greater than or equal to 10? So we can conclude, since n times p hat and n times q hat are both greater than 10, it's reasonable to assume, or reasonable to approximate, sorry, reasonable to approximate the sampling distribution of P using a normal distribution. And I'm out of breath. Questions on part A? Okay, part B. If the modern true proportion of newborn boys is 0.52, what's the probability of observing a sample proportion of at least 0.6? They're asking for the probability that p hat is greater than or equal to 0.6.
So how can you tell if it's a P hat or a P problem? Or like, how can you tell it's P hat? It's just, I don't know.
Because they asked for observing a sample proportion. P hat is sample proportion.
Okay, and what would P be?
That'd be population proportion.
Okay.
So now it's time to standardize. It says my true proportion is 0.52. 0.6 minus 0.52 divided by that square root's not going to be near big enough, so I'll write it first and then do the square root. 0.52 is my P. 1 minus P would be 0.48. All divided by 50, and I'll take the square root of this. That's the probability that Z is greater than or equal to 1.13.
Sure. Sorry for a moment. The homeworks that are for our test is 5.1 through 5.4 and 6.1 through 6.3.
Yes.
So 5.5 will not include.
Correct.
Thank you.
Which is the same as 1 minus the probability of Z being less than or equal to 1.13. Or 1 minus 0.8708, what it should be. 1 minus that is 0.1292. Questions on this one? Okay. Let's look at the next one. Suppose that a newspaper conducts a survey of a random sample of 120 registered voters. So I'm going to go and make a note that N is equal to 120. In order to predict the winner of a local election. The Republican candidate was favored by 62 of the respondents. So without even reading anything else, let's go and get P hat as being the proportion of Republican voters. So 62 over 120 gives us a P hat of 0.5167. Okay, A asks us to construct and interpret a 99% confidence interval for the true proportion of voters who prefer the Republican candidate. If it just says construct or calculate, you just have to do that. If it says interpret, I need an explanation. That was actually a common thing that was missed on the homeworks. People didn't interpret. Okay, so we want a 99% confidence interval, which means our Z critical is 2.575. Okay, let's write down our formula. So P hat plus or minus Z critical times the square root of P hat times Q hat divided by our sample size. So we said P hat was 0.5167 plus or minus 2.575 times the square root of, let's see, 0.5167 times 1 minus 0.5167 divided by N. Where's N? 120. That's always good practice to calculate your errors. 0.5167 plus or minus. And we'll do this to 4 decimal places since that's what my first one is done to. So you should get 0.1175. Which as our interval, that'd be 0.3992 to 0.6342. There's the interval itself. Now we have to interpret it. What does it mean? So we can say that we are 99% confident the true proportion of voters who prefer the Republican candidate is between, and then since election results are usually posted as a percent, let's actually put these as a percent. So they're between 39.92% and 63.42%. Repeat that one more time.
Could you just say like 60.42%? Like if you're in a real situation, not in a test. Just say 60% for the candidate because it was in your confidence window.
It depends on, honestly, at this point, what you could do is just depends on what way your media outlet leans. I mean, in all honesty, the media outlet's gonna say, you know, depending on who they want to win, that's what they're gonna tend to report. That's why on election night, you'll see like the results, and then down there in the corner, it'll say like plus or minus. And what's kind of funny on this one was when I was doing the review, I was looking at it, I'm like, well, it's not a guaranteed win because 50-50 is in the middle of that range. But now let's look at what B asks us to do. If the candidate needs a simple majority of votes to win the election, can the Republican candidate be confident of victory? Justify your response with an appropriate statistical argument. Yeah, exactly. That's what I read. I'm like, without even reading the question, I just answered the question. So, no. As we can see from part A, a significant portion of the confidence interval lies below 50%. As such, the Republican candidate cannot be completely confident of victory. Now, another thing to note, just notice how much detail I'm putting into my answer here. That's on the AP test, that's what they're going to look for. Unless you want to sign up and take the AP test and see how you do on it. Okay. Questions on that one? Okay, now let's look at the next one. At Abraham Lincoln High School, a popular achievement test is used for college placement. Counselors selected a random sample of 100 students from Abraham Lincoln High School and scored their test by hand before sending them in for computer processing. Pretty sure that's illegal. This sample, X bar equals 525 and S equals 25. Construct a 99% confidence interval for mu, the population score for Abraham Lincoln. Okay, so let's go through. We need to do a confidence interval, but we also need to make sure we know what kind of interval and if we meet the requirements. So first thing we want to check for is the population random? Or is the sample random? Yeah, so sample, we have a random sample. So we're going to note that. So we have a random sample. Okay. 2, what's our sample size? N is equal to 100, which is greater than or equal to 30. 10. Oh boy. You gotta do this to me. So,
Why is it 30?
because of the central limit theorem. There was something that was 10, yes.
That would just be.
Okay, so n is greater than or equal to 30, which means we have a large sample. Now, do we know sigma? Do they give us the population standard deviation? They give us sample standard deviation. So sigma is unknown. Which distribution must we use if sigma is unknown? That's right. We'll use the t distributions. Okay, so since we need the t distribution, we need to get our degrees of freedom. That's going to be 100 minus 1, which is 99 degrees of freedom. If we look on our table, we'll see that we don't have 99 degrees of freedom. What's the closest one we have to it? 100. So we need to use 100 degrees of freedom. And what confidence do we want? 99%. So our T, we're going to use 100. And we want 99% confidence. That value would be 2.626. I'm going to put a little note out here. Use 100. Yeah, because it's closest to 99.
So if you hit 400, that's in the middle of 1,000.
I would go without. Okay. So now let's just write our formula. It just says to construct. It doesn't say interpret. So let's write our formula out and construct it. We're going to have x bar plus or minus our t critical times standard deviation of the sample over the square root of n. Okay, they give us x bar and s up here. So x bar is 525 plus or minus 2.626 times 25 over the square root of n is the square root of 100. It's going to be 525 plus or minus 6.565. Let's just round to one decimal place. Our interval is approximately 518.4 to 531.6. Okay, questions on this one? Okay, next one. Yes. Sure. It's also posted in Blackboard, or it will be as of 5 o'clock tonight. I have it scheduled to go out. I'm recording this now, yeah. Okay, number 8. A 1976 study of smokers under 30 years of age who delivered premature babies, meaning fewer than 260 days of gestation, reported an infant survival rate of 84%. Suppose researchers would like to estimate the current survival rate. Based on the assumption that the survival rate today would be roughly similar to the rate in 1976, compute the sample size required to estimate the true survival proportion to within 0.05 with 95% confidence. Okay. So what we're estimating estimating, or we need the sample size to estimate a proportion. So what would our p hat be that's given in the problem? It'd be 0.84. What's our bound that they give us? 0.05. And then we need 95% confidence. So what's our critical value? 1.96. So to get sample size, we do n equals p hat times 1 minus p hat times our z critical divided by b squared. Plugging in what we know. Now that's 0.84. 1 minus 0.84 is 0.16. The critical is 1.96 over our bound, 0.05, and we square it. You calculate all this out, you would get 206.52. Now, on these types of problems, always round up. So what should n be? N should be at least 207. Yep, smokers. It has to be greater than 207 smokers. Now, if you put equals here, I would be okay with that. I should say greater than or equal to. I would be okay if you put equals there. Wait. Oh, it does say minimum, doesn't it? The assumptions. Sample size required. It doesn't say minimum sample size. Yeah. Okay, questions on that one? I probably would have taken the pen off on that one. Okay, next one. Next one's a little long. So many national parks and wildlife refuges and wilderness areas lie directly below designated military airspace. This raises issues of whether wildlife and, for example, loud jet noises are compatible. In an effort to evaluate the effects of low-altitude jet noise, researchers simulated these noises for captive desert mule deer. 3 minutes after the loud noises were played, the heart rates in beats per minute of these animals was measured with the following results. They give us the results. How many samples do I have here? N is equal to what? N is equal to 9, yes. Okay. Assume it's reasonable to think of them regarded as a random sample. There's one piece of information, it's random. So I'm going to write random sample here because they tell us that. Random sample. Okay, so next thing. N is less than 30, so what should we have to check for? Normality. Yeah. Now, I'm not going to have y'all calculate the z-scores. What I'll say here is that, yes, they're normal. Because you have to calculate z-scores for all of them, and we don't even know. That's going into too much detail for this. So we're going to assume normality. Now, do we know sigma? Sigma is unknown. So what distribution should we use? We're going to use the distribution. We're going to need 8 degrees of freedom. If we come down here, let's start naming what we know. We know that n is equal to 9. Our T critical value, well, that's going to be 8 degrees of freedom with a confidence of 95%. If we look on our table, that would be 2.306. Okay, now what we would have to do on this one is put these into one variable stats in the calculator. Since we're kind of running short on time, I'll go on and give you what it would say. It would tell us the mean is equal to 60.5556, and S is equal to 5.7761. For our confidence interval, we have X bar plus or minus the T critical times S over the square root of N. Why did we go to the top? So that's going to be 16.5556 plus or minus 2.306 times 5.7761 over square root of N would be the square root of 9. $60.5556 plus or minus 4.4399, which means our interval is 56.12 around the 2 decimal places to 65.00. Now, notice it says calculate and interpret. Now we've got to interpret it. we can say we are 95% confident that the mean heart rate three minutes after loud jet noises is between 56.12 and 65.00 beats per minute. And then the last part. The mean heart rate is about 51.2 beats per minute. So based on our confidence interval that we found in part A, do you think that loud jet noises have some lingering effect on the heart rate of the deer? Explain. So if their average heart rate is 51.2 beats per minute, do the noises tend to affect them based on what we found? Yes. That's what we'll say, yes. The data suggests that the heart rate of deer exposed to the jet noise is higher than expected. Since the value of 51.2 is below our calculated interval. Okay, that's the review. Just in time. 3 minutes for the bell. So I'll be in here after school. I'll be on Collaborate after school. If anyone needs help, please come by and see me.